All right, guys, so this is your big idea for frequently asked questions, your review questions. So for the first problem, I gave you this reaction, and I told you that you had 30 mils of hydrochloric acid, and it was 1 molar hydrochloric acid, and then I said you have 0.56 grams of iron. And the most important thing for you to realize for this problem before you get started is recognizing the fact that this is going to be a limiting reactant problem. So, and the reason why it is because I give you reactant, I give you two different amounts of reactants. I give you HCl and I give you iron. So to answer this question, to figure out what the limiting reactant is that you first have to figure out how much product each of these reactants will produce. So I'm going to start out with HCl. I'm going to convert my volume into liters. And I'm now in moles of HCl. And then I can easily get into moles of, well, I'm just going to get into moles of either product because both of these are 1-to-1. So I'm just going to put 1 mole of product here because why not? And that's for every 2 moles of HCl. And so what you end up getting when you do the math, you get 0.015 moles of product. Okay, if I did the same thing but for iron now, well, how many moles of product will iron form? I'm going to first get into moles of iron by dividing by the molar mass. Get into moles of product. Moles of iron. It's 1-to-1, and so the answer you get is 0.010 moles. Now I didn't need to get into grams because whichever one produces the smaller amount of moles of product, that is your limiting reactant. And so iron in this case is going to be my limiting reactant because I only produced 0.010 moles of product. Okay, so that's my answer for that. What volume is formed? Well, if you notice the temperature and pressure here, that is STP, standard temperature and pressure, 0 degrees Celsius and 1 atmosphere. That's STP. So at STP, I know that the volume is going to be 22.4 liters for every 1 mole of gas you have. So if instead of just saying product, I said, okay, I've got H2, then it'd be 0.01 moles of H2 times 22.4, and I could get my answer there. Then it says, how do you determine how much excess reactant is left over? Well, I know this amount of product is formed, so I could take this and plug it back in and figure out, okay, how many moles of HCl, my excess reactant, were actually used to produce this. Because if I used all my HCl, I would have produced 0.015, but I didn't. I produced 0.010 moles of product. So I'm going to get this back into moles of HCl. So that gives me 0.020 moles of HCl. Well, how many moles of HCl did I start with? If I multiply these, I started with 0.03 moles of HCl. I used 0.020, so what's left over? 0.010 moles. Okay. For the next problem, it says if oxygen is represented by the large black dots and H2 by the gray dots, mine kind of look black, sorry, draw the contents of the box after the reaction proceeds to completion. So I'm going to really quickly write out my reaction. Oxygen reacts with hydrogen gas to produce water. I balance this. So I know for every 1 mole of oxygen, 2 moles of hydrogen are going to be used, and 2 moles of water are going to be used. So I start with 2 moles of hydrogen here. I've got 2 H2s, which means H2 is actually, since I start with equal amounts, equal numbers of moles of O2 and H2, 2 and 2, then I know that H2 is going to be my limiting reactant because it is going to limit how much product can be formed. And if you want to see the math for that, if you just want to create an ice chart, for example, obviously this isn't concentration, but it's just the number of particles. Then if 2 hydrogens react completely, then because this is a 2-to-1 ratio, then I know that only 1 oxygen, so oxygen is going to be in excess. Okay, so I know all of my H2s are going to be reacting. I know that I'm going to have 1 oxygen left over. And then the other thing that's going to form because this is a 2-to-2 ratio, I'm going to form 2 waters. Okay? So stoichiometrically, that's how you do it. If you actually just want to count your number of atoms, I've got 1, 2, 3, 4 oxygens, 1, 2, 3, 4 oxygens, 4 hydrogens, 1, 2, 3, 4 hydrogens. So that's how I know I can double check my answer. For number 3, what is the difference between an intermediate and a catalyst? Does it matter in which step the intermediate is formed and then used up? So remember, an intermediate is going to be created and used up over the course of the reaction. And the answer to the question of, does it matter what step you form the intermediate and in what step it is used up? The answer is no, it doesn't matter. As long as it is created in the reaction and used up in the reaction, it is an intermediate. It doesn't matter what step it happens in. A catalyst exists at the beginning of a reaction. And it remains unchanged. And the only reason why a catalyst is added is to speed up a reaction. So really quickly, when you are adding reactions in your individual elementary steps together to get an overall reaction, both your intermediate and your catalyst will actually cancel out. The important thing for you to know, when you're writing out your rate law, your intermediate, remember, you cannot include in your final rate law. You can include a catalyst in your final rate law. That's fine if it applies. Okay. For number 4, it says, does the amount of bumps in the potential energy graph depend on the number of steps? Yes, absolutely. So if I have a potential energy curve that looks like that, I've got 1 step. If I have a potential energy curve that looks like that, it's 2 steps. If I had 3 bumps, it would be 3. The most important thing for you to know, once you go beyond 1 step, whichever hump has the higher activation energy, so this is the activation energy for this first hump, this is the activation energy for the second. The one with the higher activation energy, that is going to be your rate determining step or your slow step. Okay? All right, for number 5, how can the rate of reaction increase? So there are 4 different factors that we've looked at. The first is surface area. So your reactants, you want to maximize surface area to maximize collisions. Okay, so the more surface area it has, the more effective collisions you will have. So a solid, if you have a solid chunk, that's going to have a much smaller surface area than if you, for example, have a powder. The best is to actually have an aqueous solution. If your compound is dissolved in an aqueous solution, it's going to have way more surface area to be able to react. The next one is temperature. So the higher your temperature, the higher your rate is. And that's because you're going to have more collisions and they're going to have enough energy to overcome the activation energy. Okay. There was a question with respect to, does this fact, the increase in temperature, have to do with orientation? Remember, for a reaction to be, a collision to be an effective reaction, you not only have to have enough energy, you also have to have the correct orientation. This does not have to do with orientation. Okay, the speed at which the molecules hit one another is extremely important, but that doesn't dictate whether or not they're going to have the correct orientation. Temperature doesn't apply to that. The other, you also want a high concentration of reactants. The higher your concentration of reactants, the higher your reaction rate, which is why as a reaction proceeds and you lose reactants, the rate of that reaction is going to slow down. And then finally, if you add a catalyst, what it does, and you can see in the curve here, it'll just lower the activation energy and therefore make the reaction faster. Okay? All right, next set of questions. So I was asked, can you review how to determine the hybridization of an atom? Absolutely. So what determines the hybridization of an atom is the total number of electron domains. Okay, so for example, if I have something that has a total of 4 electron domains, okay, so that could be, so I'm going to put bonding domains and non-bonding domains. So if I have a molecule that has 4 bonding domains and 0 non-bonding domains, what that means is that its shape is going to be tetrahedral and its electron domain geometry is going to be tetrahedral. So for example, if I had, well, I'm just going to draw a generic one, but it could be like CH4 or something like that, okay? This is going to be sp3, okay? If I have something that has 3 bonding domains, 1 non-bonding domain, its geometry is going to be pyramidal, like that. But still, because it has a total of 4 electron domains, it's going to be sp3. If it has 2 bonding, 2 non-bonding, it still has 4 total electron domains, therefore it's still going to be sp3. If it has a total of 3 electron domains, okay, let's say it's 3 bonding, 0 non-bonding, so it would look like that. So that would be trigonal planar, okay? And actually it would have a double bond, okay? Then it would be sp2. Remember, this is just one bond, a double bond is just one bonding domain, sp2. If it has, and I'm going to go over here, if it has 2 bonding, 1 non-bonding, so it would look something like this. Okay, again, it's going to be sp2. You got 1, 2, 3 total electron domains. Okay, if you have a total of 2 electron domains, so in all likelihood you'd have 2 bonding, 0 non-bonding, so it would look like this, then that would just be sp. And then the same thing applies for an expanded octet. I'm not going to get into that. So if you have a total of 5 bonding, or 5 total electron domains, bonding and non-bonding added together, it would be sp3d. If you have a total of 6, it would be sp3d2. Okay. How do we represent the heat in a chemical reaction? What about the potential energy curves? So for heat in a chemical reaction, if your delta H is on your reactant side, then it's going to be endothermic. If it is on your product side, it is exothermic. Okay. For potential energy curves, I would represent this an endothermic reaction like this, because the energy, so this is endothermic, the energy of my products is higher than the energy of my reactants. Meanwhile, this would be exothermic. Okay. How can you calculate the rate of a reaction? What is the difference between rate of appearance and rate of disappearance? Okay. So how do you calculate the rate of a reaction? They were asking with respect to changing concentration. So let's say, for example, first of all, your rate is going to be your change in concentration over your change in time. Okay, so change in concentration, what you're going to do is you're going to take your final concentration, and from it, you will subtract your initial. And same thing for your time. Final minus initial. So let's say, for example, at time 0 seconds, I have, I don't know, 2 molar solution, and then at 20 seconds, I have a 1 molar solution. So what that means is that my final concentration will be 1.0 minus 2.0 divided by 20 minus 0, 20 seconds. So that's how I would calculate my rate. Notice my units would be molar per second. Okay? So is this rate of appearance, rate of disappearance? Well, notice I am losing concentration. I'm decreasing my concentration. This value would be negative. So this is actually going to be your rate of disappearance. If your rate is negative, it is disappearing. If instead I was going from 1 molar at 0 seconds to 2 molar at 20 seconds, then this would be 2.0 minus 1.0, right, divided by 20. In which case, this would be my rate of appearance, because I would be increasing the amount of my concentration. Okay. There was a question about your Beer's law. Absorbance equals ABC. So keep in mind, A is your absorbance, how much light your substance is actually going to absorb and prevent from transmitting. It has no units. So that was another question someone asked. No units for that. Little a is your molar absorptivity. That is a constant that depends on the substance in question, and it will never change. So it is always the same. B is your path length, and that is simply going to be the width of your cuvette. So you can change that if you change the type of cuvette that you're using. Okay, and then C is your concentration, which is measured in molar. Keep in mind here, so Y would be your absorbance, AB is going to be your slope, C is your X value. This plus B simply represents sources of error. So in your lab, you got a B value, and that's simply because you had experimental error. All right, for number 10, when given the properties of a compound, how can you use that information to predict characteristics of a different compound? So this question referred to, you were given this nonpolar molecule and told that it was non-flammable. And then you were asked what molecule would also most likely be non-flammable. Well, if I know that this nonpolar compound that has halogens as its outside atoms is non-flammable, I would probably look for a nonpolar molecule that also has halogens as its outside atoms. You're looking for just similarities in the atoms themselves and the structure of the molecule, and that will then relate to similarities and characteristics like it being non-flammable. For 11, how can you calculate mass percent? So remember, mass percent is the mass that you are concerned about, so mass of interest, and this can be the mass or this can be the molar mass, okay? Doesn't matter. And then you're going to divide by the total mass, and you'll multiply by 100%. So for example, if I say, hey, what is my mass percent of water? Let's say I have 10 pounds of water in me, which is low, and let's say I weigh 125 pounds, right? You take the mass of what you're concerned about and divide by the total mass. Well, what if I said, what is the mass percent of sodium oxide? Okay, and not just what's the mass percent, so what is the mass percent of sodium in sodium oxide? Well, for sodium, that would go on, the mass of sodium would go on top because that's what I'm asking about. What's the mass percent of sodium in sodium oxide? So I would take the molar mass of sodium times 2 because there are 2 of them. I think it's 22.9 something, don't hold me to it. And then I'm going to take the total molar mass of this compound, and then I would multiply by 100. So keep in mind, if you're wanting to have a higher percent of, let's say, for example, sodium in a compound, you want the total molar mass, the value on bottom, to be as small as possible. So if you're choosing an anion to have instead of oxygen, you want the anion to have the smallest molar mass possible, so that when you're dividing by a smaller number, and therefore your mass percent is going to be larger because the value on bottom is smaller. For number 12, what factors change the rate constant? So there are actually 2. I'm going to really quickly talk about them in a second, but someone asked, what does the rate constant measure? So remember, if you're writing out your rate law, rate equals K times your concentration. It can be concentration squared or concentration squared times another concentration. K simply helps you relate concentration and rate. It's your go-between. It's your constant that allows you to convert from concentration into rate, or to see how a change in concentration will affect your rate. Okay, so factors that change your rate constant. 1, if you increase temperature. Okay, so obviously increasing temperature increases your rate, but if you notice, if you look at your rate law, temperature isn't changing your concentration, so it must be changing your K. So if you increase temperature, that means it increases your K value. The second one is adding a catalyst. So a catalyst speeds up your reaction rate. Okay, clearly it doesn't affect the concentration of your reactants, which means adding a catalyst must also increase your rate in order to increase your rate constant in order to increase your rate. So increasing temperature and adding a catalyst increase your rate constant, which then causes your rate itself to increase. Okay, how can we calculate half-life? All right, so really quickly, remember you've got two different equations that we've looked at. This is for a first order reaction. First order. And these are on your cheat sheet, by the way. This is a second order. Okay, so how would I figure out the half-life? Well, remember the definition of a half-life is the time it takes for half of a reactant to react. Okay, so let's say, for example, my initial concentration, I don't know, you can make up a number. If you want it to be 100, make it 100. If you want it to be 1, make it 1. I'm going to make this 1, because why not? So that means that my half-life would occur once I have half as much reactant, which means my concentration would be half. So if you then solve for the time required for your initial concentration to go from 1 to a half, or from 100 to 50, or 4 to 2, or whatever you want, that would be your half-life. Same thing here. You plug in 1 here and a half here, and you can figure out your half-life. Now, the really cool thing for first order is if you actually plug this in and solved for it and isolated your half-life, your time, what you would end up getting mathematically, ln of 1/2 minus ln of 1, what that equals is 0.693. And so that's why, or negative 0.693. So that is why we can have the equation that my half-life is 0.693 divided by my K. Now keep in mind the only reason why I can use this is because regardless of what initial concentration I plug in here, my half-life, the time required for a half of it to react, is going to stay the same. That's the definition of a first order reaction. Here, I can't create a simple formula because my half-life depends on the initial concentration. So if this changes, that's going to actually change my half-life. So this is why I can use this for first order, because my half-life does not depend on the initial concentration. Okay. What are the units for absorbance? We just went over that. There are no units. And what are the units for rate? So remember, rate is change in concentration, so molar, per unit of time. So if it's seconds, if it's hours, if it's minutes, the question was, how strict are they about that? They're very strict, because saying that the change in concentration per minute is the same thing as per second is completely wrong. So they're going to be very strict, so make sure that whatever unit of time, seconds, minutes, hours they're using, that you are recording that properly. Number 15. This is a question that a lot of people struggle with because, well, I'll show you why. But I'm asking for you to write the rate law. So notice, first of all, I've got a bunch of times 10 to the negative whatever. So in order to get rid of that, remember, I want to multiply by something that's going to get rid of all the decimals. So I'm going to multiply all of these by 10 to the 4th, because what that does is that makes this 4.3. That makes that 13, right? Because 10 to the negative 3rd times 10 to the 4th is 10, so that'll make that 13. That's going to be 53, and that's going to be 80. So that makes my life a lot easier. Now, I see from step, and I'm going to explain it verbally. I want you guys to write out the explanation. From experiment 1 to experiment 2, my concentration of A triples, and my rate triples, which means it is first order with respect to A. Okay? But now I need to figure out the order for B. I don't know it. Here's why this is tricky. Notice my concentration of A never stays constant, which means I can't easily just see what happens to my concentration of B and then compare that to what happens to my rate. So what I'm going to have to do is I'm going to take 2 trials. So I'm going to go from experiment 2 to experiment 3. And what you notice is for A, the concentration doubles. I know it's first order. So that's from 2 to 3. From 2 to 3, B also doubles. And my rate goes from 13 to 53, so it quadruples. So this forces you to figure out the order of B without A staying the same. Well, since A is doubling, just look at the basic math here. What would the order of B have to be in order for the rate to quadruple? Well, B is also going to have to be first order. So my rate, therefore, is K times A times B, which is first order. Let's say, for example, instead of it quadrupling, let's say, for example, it increased by a factor of 8. So A doubled, its first order. B doubled, but I don't know its order. And the rate increased by a factor of 8. Well, here now, how would I solve that? What would my x be? Well, 2 times 2 to the what equals 8. So B would be second order for that one. Okay, let's look at another tricky one that I gave you. For 16, I'm going to figure out my rate law. So please write your explanations in here. I'm just trying to go as quickly as possible. I want to get rid of these really quickly, so I'm going to multiply everything by 10 to the 4th. So this is going to be 10, okay, because I multiplied by 10 to the 4th. Now I'm going to figure out the rate for NO first. It doubles while O2 stays the same. My rate doubles as well, which means it is first order with respect to NO. Let's figure out O2. So NO stays the same between 2 and 3, so I'm going to look from here to there. Notice that my concentration quadruples. So I'm going to just write this down here. My concentration quadruples, but my rate only doubles. Well, crap. I haven't seen anything like this before. 4 to the what equals 2? Well, a half. So yes, you can have a reaction order that's a half. Do you know what the graph would look like? No. You only know what the graph would look like for 0 order, first order, and second order. Not for third, not for half, not anything else. But you can still do the math and figure that out. Okay, the next question, what is the rate law for a 0 order reaction? Well, if it's 0 order, I know that the concentration doesn't affect the rate. So the only thing that would be involved would be K. And keep in mind, since I only have K and I have no concentration, the units for my K, the K value that I get, are just going to be the units for your rate. So molar per second, or molar per minute, or molar per hour. Okay, so what a 0 order reaction is telling you is the rate does not depend on the concentration of your reactants. You will rarely see a truly 0 order reaction, but that's what it is. When completing a spectrophotometry lab, if we were delayed in putting the cuvette in the machine, how would that affect the rate of disappearance? Well, if you think about it, as the reaction proceeds, okay, if this is rate, remember the rate of the forward reaction is going to slowly decrease until it reaches equilibrium. Okay, the rate of the reverse reaction will slowly increase until it reaches equilibrium. Now the rate of the forward decreases because you are losing reactant. So if you paused and didn't immediately put the cuvette into the machine, even the delay that you naturally had, instead of your rate starting here, you're probably going to start right here because all of this reaction would have already occurred before you put it into the spectrophotometer. So the rate of your reaction, the rate of your disappearance would have decreased. And the absorbances would be lower than you would expect, and the concentrations would be lower than you would expect. So you really want to minimize the delay and prevent a lot of the reaction from occurring. 19, what graphs can we use to determine the order of reaction? So, for 0 order, concentration versus time, you're going to have a negative linear slope. If it's curved here, It's not zero order. That's the only thing curving tells you. It is not what you think it is. Okay? Then, so that's for zero order. For first order, you're going to do natural log of your concentration versus time. Okay? It's going to be a negative linear slope. If it's curved, it's not first order. Okay? The slope of this, okay, is going to be your K. So your negative K, because remember K can't actually be negative, and the slope of this line is negative. So whatever the slope of this line is, that is your K value, just the negative of it. Second order, one over concentration versus time. It's going to have a positive linear slope. The slope of that will be your K value. Okay? Third order, we never created a graph for that. You just need to know these three. Concentration versus time, negative linear slope. ln versus time, negative linear slope, then it's first order. 1 over concentration versus time, positive linear slope, it's second order. If it's curved for any of these, it just tells you if it's curved for this, not zero order, not first order, not second order. You can't use a curved slope to try and determine the order of a reaction. Okay, last page. Can you explain the Maxwell-Boltzmann curve and how activation energy is represented in it? So if I were to create a Maxwell-Boltzmann curve, remember your y-axis is simply number of atoms. Okay, and then if I put kinetic energy on my x-axis, someone asked about the activation energy line. So basically this line represents the energy needed for a reaction to occur. So if you're above this point, then the reaction will occur. If you're below it, then those particles don't have enough kinetic energy. Okay, so then if I'm going to show this for different temperatures, so I've got an atom with a certain temperature. This would be low because its peak is at a lower kinetic energy. Let's say this is 0 Kelvin. The next one would be, let's say, 10 Kelvin, right? So the higher your temperature, the higher your kinetic energy. Let's talk about what all of these mean. So remember, you pull the string and it makes these wider. So a couple of things they grade based on. First, the peak needs to be farther to the left if you're at a lower temperature, and then the higher your temperature goes, the further your peak is going to be to the right. The second thing you need to notice that the overall, the width of it increases, and what this part represents, notice here, these are the only particles that have enough energy to overcome the activation energy for a 0 Kelvin, for anything that's at 0 Kelvin. Notice here, all of these within this curve from here on have enough energy, and then for these, all of these guys have enough energy to overcome the activation energy. So what that's telling you is the higher your temperature, the more particles you're going to have with enough energy to overcome the activation energy, which is what we've said. So be careful in how you draw this. Make sure that your peak is to the right if you're at a higher temperature, and the distribution is greater so that when you're looking at the activation energy, there's going to be more particles that have enough energy to overcome the activation energy. Another way to draw your Maxwell-Boltzmann diagram is to have velocity as your x-axis, in which case I then can compare the size of my atoms. So this would represent a very large atom or molecule because it has a low velocity because it has a big mass. This would be a medium-sized one, and that would be a small-sized one. So those are just some Maxwell-Boltzmann curves for you. Okay. Okay. Number 21. Oh, and there's, sorry, it was a little bit blurred, but there's all of your work right there. Okay, so you can see fewer particles, more particles, even more particles as your temperature increases. So just get comfortable drawing those. How do you know when the pH increases or decreases over the course of reaction? So if I have a reaction, I'm going to show a bunch of different reactions. Okay. If a reaction occurs, reactants, products here, if I start with H plus and it's used up and doesn't show up in my products, then I know that the pH had to increase because I lost H plus. Okay, if I started with OH minus and I lost OH minus over the course of the reaction, then that means that my pH decreased because I'm losing OH. If H plus is formed during the course of the reaction, then I know that my pH decreased because it's becoming more acidic. If I formed OH minus, I know my pH had to increase because my solution is becoming more basic. And keep in mind, H plus and H3O plus are synonymous. Okay? Write the rate law for the following reaction. So if it were a slow step, that would be super easy to do if my first step were a slow step, but it's not. So what I'm going to first do is I'm going to write out my rate law using the slow step. So K times Cl times CHCl3. Okay. Then I would say in my explanation, because Cl is an intermediate, it cannot remain in the rate law. Okay. Therefore, since step 1 is in equilibrium, what I can say is that the rate of the forward, so K times Cl2, equals the rate of the reverse. Okay? And then you can replace Cl, okay? And just be careful because you need to square root both sides. So I would show that work. And then I would say rate equals K times my concentration of Cl2 to the 1/2 times the concentration of CHCl3. And I am done. That works as an explanation. Okay. If you were just given, let's say, for example, I'm going to change this problem. What if this were step 1? And they said, what is the rate law? Then I would just write out this rate law. That would be my answer. But then if they asked for me to explain, I would say that you used the stoichiometry of the slow step. Okay? Basic math helps. So how would you do this work right here? So what I would do, because it's 1.04 times 10 to the negative second divided by that, I can multiply both of these by a certain value. So why wouldn't I just multiply them by 10 to the third? Remember, you want to multiply by the larger exponent. So I'm going to multiply by 10 to the third, so that would make this 10.4 divided by, multiply by 10 to the third, 5.2. And so you would end up getting just 2. Okay. Comparing bond polarities by using electronegativity. So remember, when we're talking about a bond, we're talking about a covalent bond. And these two atoms are going to be sharing electrons. So the polarity of it basically is just a measure of how equally they share it. So if the electronegativities are similar, then the bond polarity is going to be very low. If the electronegativities are very different, then your bond polarity is going to be very high. Remember, the farther the distance between the atoms on the periodic table, the greater the difference in electronegativity. So that's why, for example, this is extremely polar and allows you to have hydrogen bonding, because the difference in electronegativity between nitrogen and hydrogen, or oxygen and hydrogen, or fluorine and hydrogen is very high. Okay. 25. Does doing anything to steps that aren't the rate determining step affect the rate of the reaction? What they were basically saying is, you know how I say you can lower the activation energy. If I add a catalyst and it lowers the activation energy of a slow step, then it's going to make the reaction faster. Yes. If you do anything to a fast step, it will not affect your reaction rate. So if you add a catalyst to a fast step, it's going to have no effect. Because remember, it's your slow step. This step that has the high activation energy, that is what dictates the rate of the reaction. And so no matter whatever concentration of, I think they meant to say a reactant that you add or adding a catalyst. It won't have any effect unless you're adding it to your rate determining step. For 6, if a reaction reaches completion, does that mean the concentration of reactants will equal 0 and the rate of the forward reaction will reach 0? The answer is no. No matter the degree to which a reaction proceeds, you will not produce only Y, because every reaction, no matter how high your K is, right? If it's 10 to the 34th and you're like, yeah, my products are super favored, that is true. But regardless of how high your K is, Y will always you will have a small reverse reaction, which will always be producing just a tiny bit of X. So your reactants will never reach 0. You're always going to have a tiny bit of reactants, and therefore, since you're always having a tiny bit of reactants, the rate of your forward reaction will never actually reach 0. That being said, the rate of your reverse reaction, initially, when you only have X and you have no Y at all, then yes, the rate of your reverse reaction starts out at 0 molar per whatever unit of time. And that's just because you have no products to begin with. But after that point, once you start, then you will always have some sort of a forward and some sort of a reverse reaction.